Hello everyone, welcome to Chemistry Academy. This is JEE Advanced series where we discuss question to improve your rank in JEE Advanced. Hope this is useful to you. Don't forget to like the video. For more such content, you can download our app. So this is episode 24 of JEE Advanced problem series, and this problem is based on electrochemical equilibria. This question can be framed in numerical value problem, and this is taken from preparatory problem of ICHO. So I'm going to read out the problem first, and then you can pause the video and try to solve the question by your own. They have given the value 2.303 RT upon F is equal to 0.06. The problem first part is calculate the standard electrode potential for the aqueous couple FeCN6 3 minus oblique FeCN6 4 minus from the following data. So here iron is present in +3 oxidation state, and this iron is present in +2 oxidation state. So there is gain of electron by this chemical species in order to convert into this chemical species. The data for the reduction potential of iron +3 to iron +2 in aqueous state is given, that is 0.77 volt, and Fe3 plus in aqueous state plus 6 times of Cn minus in aqueous state will form this complex ion. So this reaction is formation of the complex ion, K formation. The value of log equilibrium constant for the reaction is given. Similarly, Fe2 plus will combine with 6 times of Cn minus to form this complex ion. So this is the reaction of formation of this complex ion. Central metal and ligands will combine to form this ion, and log equilibrium constant value is given. So log here 10 is the base, right? So log 10 Kc means the value is given for the equilibrium constant. The following standard electrode potential have been reported. So this is the first part, right? Now this second part is indium +1 in aqueous state will accept 1 electron to form indium metal in solid state, and E0 for this reaction is -0.13 volt. Indium +3 will accept 3 electron to form indium metal. E0 value is -0.34 volt. Thallium +1 will accept 1 electron to form thallium metal. E0 value is -0.34 volt. And thallium +3 in aqueous state will accept 3 electron to form thallium metal. E0 value is 0.72 volt. So the second part is, this is the data for the second part. The second part is calculate the equilibrium constant for the disproportionation reaction for indium and thallium and comment on the result. So let us solve the problem one by one. So this is the first part of the problem, calculate the standard electrode potential. So we should write the reaction for which we have to calculate the standard reduction potential or standard electrode potential. क्या है? आयरन पहले +3 ऑक्सीडेशन स्टेट में है, इस कॉम्प्लेक्स आयन में FeCN6 3 minus in aqueous state. Iron is present in +3 oxidation state. It will accept 1 electron to form this complex ion FeCN6 4 minus ion in aqueous state. तो इसको हम क्या लेते हैं? This is reaction number 1. We have to find out E0 of this reaction with the help of the given data. तो इस डेटा को भी अगर हम रिएक्शन के फॉर्म में लिखें, तो आई कैन राइट दैट द फर्स्ट रिएक्शन हियर, आयरन +3 in aqueous state will accept 1 electron to form iron +2 in aqueous state. This will be iron +2 in aqueous state. This is reaction number 2. Now, since we want FeCN6 4 minus on the right hand side, right? This is given here. So FeCN6 4 minus, and we want FeCN6 3 minus on the left hand side. So I'm writing the number of the equation here. Let me rewrite the given reactions. Fe3 plus in aqueous state plus 6 times of Cn minus in aqueous state is in equilibrium with FeCN6 3 minus in aqueous state. This is reaction number 3. Similarly, I can write that iron +2 in aqueous state plus 6 times of Cn minus ion in aqueous state will form the complex ion FeCN6 4 minus ion in aqueous state. These are the reaction 1 to 4. I have to calculate the value of 1 in terms of these reactions. So I'm going to use thermodynamic operation which we used in thermochemistry. So in this, we try to write the first reaction in terms of second, third, and fourth. So here FeCN6 4 minus is there on right hand side. FeCN6 4 minus is there in the fourth reaction on the right hand side. So I will write the fourth reaction as it is. Then FeCN6 3 minus is there on the left hand side. So in order to make this on the left hand side, I should subtract it. By doing so, like by writing the reaction 4 as it is, Fe2 plus is in left hand side. I don't want Fe2 plus. So what I can do, I can add a reaction 2, because by doing that, this Fe2 plus will cancel out. When I'm subtracting this reaction, when I'm putting minus sign in front of third reaction, so this iron plus 3 will go on the right hand side. So this iron plus 3 will cancel out. So we'll get the first reaction with the help of this thermodynamic operation. Now I have to put the value. I should write that delta G01 is equal to delta G04 minus delta G03 plus delta G02. So now I can put the value delta G01. So this delta G01. So this is a half cell reaction. I can write that delta G0 is minus NF E0 of the cell, right? So here I can write that this value is number of electrons participating in this reaction is equal to 1, and Faraday constant into E01. On the right hand side for this fourth reaction, this is the fourth reaction, I can write that delta G04 is equal to minus 2.303 RT. Why I'm taking 2.303? Because they have given the value of log. So base is 10 here. That's why I'm writing in this form. RT log equilibrium constant for the fourth reaction, right? So I'm writing here K equilibrium for the fourth reaction. And this for the third reaction, this minus and minus will become plus. So I can write that this is 2.303 RT log equilibrium constant for the third reaction. And this is a half cell reaction. Iron plus 3 is converted into iron plus 2 by accepting one electron. So minus number of electron is 1 into Faraday constant into E0 of the reaction number 2. Right, we have put this as reaction number 2. So E0 for the reaction number 2, we can put the value over here. So if I take this minus F on the right hand side, I can write that E01 is equal to this minus and minus will become plus. So I can write 2.303 into RT divided by Faraday constant. And this log equilibrium constant value they have given, this value is 36.9. Here also I can write, but here when I take this minus sign, it will become minus 2.303 RT divided by Faraday constant log equilibrium constant 3 value, which is 43.9. This minus and minus will become plus. Faraday will cancel out. E02 value already is given, that is 0.77 volt. So from here, if I put the value of 2.303 upon into RT upon F, which is given as 0.06. So I can put the value over here. This value is 0.06. I can take 0.06 common here and here. So it will be 36.9 minus 43.9 plus 0.77 volt. So by simplifying this, I can write that this value will be 0.06. And the difference of these two numbers, 0.9, will cancel out. So 43 minus 6 will be 7. So this is minus 7. So minus 7 into 0.06 plus 0.77. So on further simplification, I can write that this is minus 0.42 and this value is 0.77. So this is coming plus 0.35 volt. So this will be the answer, E0 for this half cell reaction. That is where iron from +3 oxidation state in this complex ion form is converted into iron to +2 oxidation state is this value. Right, so this is the first part which we have solved. Now let us move for the second part. Second part is calculate the equilibrium constant for disproportionation reaction. 3 times of M plus in aqueous state will form M3 plus in aqueous state plus 2M in solid state. So if you look the data, they have given the reduction potential of indium +1 and indium +3. So when we are discussing the disproportionation reaction, first we are discussing about indium. So for indium, if I am writing what is the disproportionation reaction, I am putting the value here in place of M plus, I am writing indium plus. So 3 times of indium plus is converted into indium plus 3 in aqueous state plus 2 times of indium metal in solid state. So when I am discussing about this disproportionation reaction, I can write that this is the reaction which is taking place at anode. We can write that oxidation half cell reaction. I can write indium from +1 oxidation state is going to +3 oxidation state by loss of 2 electron. So this is the oxidation reaction, and at cathode reduction will take place, right? So the reduction half cell reaction, I can write that indium in +1 aqueous state will accept 1 electron to form indium metal in solid state. In order to balance the overall reaction, will make the electrons equal, so we have to multiply this by 2 and then we can add these two reactions. So on adding the reactions, we'll get that overall reaction is 3 times of indium in +1 oxidation state is converted into indium plus 3 in aqueous state plus 2 times of indium metal in solid state. This is a galvanic cell, right? So for this galvanic cell, if I write that what is E naught of the cell, E naught of the cell is equal to E naught oxidation plus E naught reduction. Oxidation में क्या लिखेंगे? Indium from +1 oxidation state is moving to +3 oxidation state. Reduction में we should write that indium from +1 oxidation state is moving to metallic form. So if I know these values, like here they have given that indium metal to indium +3, right? This value we know, but we don't know this value. So for that, we should draw the diagram to solve it. Indium is present in +3 oxidation state. Indium should go in +1 oxidation state, and finally it should go to metallic form. Indium +3 to indium, this value we know. We have to calculate this value, right? So with the help of this diagram, we can easily calculate the value. This value is given. ये value दे रखी है. +3 to metallic form is -0.34 volt. This we have to calculate. We can assume this is X. Indium +1 to 0 oxidation state, this value is -0.13 volt. So those who know about these type of diagrams, they are very helpful, right? So these are also based on Gibbs free energy is additive in nature. So here if I calculate that what is the number of electrons participating, this is E naught 1 and this is N1. N1 number of electrons participating is 2 here, and the number of electrons participating here is 1, and the number of electrons participating here is 3. So I can write that N1 E naught 1, that is 2 times of X, plus N2 E naught 2, that is minus 0.13 volt, is equal to N3 E naught 3. So 3 into minus 0.34 volt. From here I can calculate what is the value of X. We can write that 2 times of X is equal to 0.13. इसको right में ले गए और इसको multiply करते हैं. So that is 12, 1.02. So if I subtract this value from here, we can write that 1.02 minus 0.13. So 12 minus 3 will be 9. So 0.89. So now from here, if I write that what is the value of X, the value of X is equal to 0.445, right? So the value of X is coming 0.445. So once we know the value of X, now we can calculate what is the E naught of the cell. So I can write that the E naught of the cell is equal to E naught reduction of indium +3 to indium +1 to indium +3, oxidation potential. This potential is reduction potential, what we have calculated, right? So now I have to write the reverse of that. So minus times of X I have to write. So let me write here. E naught cell is equal to E naught of indium +1 to indium +3 plus E naught of indium +1 to indium. So here if I put this value, we have calculated reduction potential. If I write oxidation potential, it is minus 0.445 volt. And E naught of indium plus 1 to indium, already we know this value. Indium plus 1 to indium is minus 0.13 volt. This value is minus 0.13 volt. Here when we are solving, the net value should be negative, right? So we have done sign error over here. This will be, so on solving this, we are getting that this value is minus 0.89. So this x is equal to minus 0.445. Now we can calculate E naught of the cell. So E naught of the galvanic cell is equal to oxidation electrode potential plus reduction electrode potential. This we are getting plus 0.445 because we have calculated the reduction potential, but here we have to write the oxidation potential, and this value is already given, that is minus 0.13 volt. If I further simplify, I can write that this value will be, we can write here 5, and this will be 1, and this will be 3. So 0.315 volt, that is E naught of the cell. Since E naught of the cell is positive, it means that the disproportionation reaction is spontaneous. So this is the first part. Disproportionation of indium is a spontaneous process. In the same manner, we can discuss the second part. So in case of thallium, already we know that thallium in +1 oxidation state is more stable. So if I write that, what is the disproportionation reaction? If I write the reaction taking place at anode, that is oxidation reaction. So thallium in +1 oxidation state in aqueous medium will go to thallium in +3 oxidation state in aqueous medium by loss of 2 electron, and at cathode reduction will take place. We can write that thallium +1 in aqueous state will accept 1 electron to form thallium metal in solid state. So in order to balance the overall reaction, we have to make the number of electrons equal, and then we'll add these two reactions, right? So from here, if I write that what is the E naught of the cell, I can write that that is equal to E naught oxidation of thallium +1 to thallium +3 and E naught reduction of thallium +1 to thallium. So here this data is not given, and that data can be calculated with the help of electron diagram. If I write in decreasing order of oxidation number, thallium from +3 oxidation state will go to thallium +1 oxidation state and then thallium. This data is known. So this is E03. E03 value is plus 0.72 volt, right? And the number of electrons from +3 to 0 oxidation state, so N3 value will be 3. We have to calculate this value E naught of this reaction. So this is why the number of electrons participating here is 2, and this value is given thallium +1 to thallium. This value is minus 0.34 volt, and the number of electrons participating in this reaction is equal to 1. So from here I can write that 2 times of Y minus N2 into E naught 2 is minus 0.34 volt, and this is 0.72 into 3. So if I simplify from here, I can write that 2 times of Y is equal to 0.34 plus this will be 6, so 2.16. So if I add this value is coming 2.50 volt, and from there we got that the value of Y is equal to 1.25 volt. Now I have to calculate what is the E naught of this disproportionation reaction for this galvanic cell. So thallium +1 to thallium +3. This is thallium +3 to thallium +1. So minus times of Y. So this is minus 1.25 volt. And this value is given. This is minus 0.34 volt. So from here, if I calculate, this is coming negative, right? So E naught of this galvanic cell reaction, that is disproportionation reaction, if you see, this is coming negative. So if I add these two, I'm getting this value as 1.59 volt, minus 1.59 volt. So the negative sign is saying that disproportionation reaction is non-spontaneous. So from here we can say that comproportionation is reverse of disproportionation, right? So comproportionation reaction is spontaneous. So from here we can prove that because thallium plus 1 is more stable than thallium plus 3. So we can say that if thallium is present in plus 1 oxidation state, it is not going to disproportionate. So the disproportionation reaction of thallium plus 1 is non-spontaneous, while the disproportionation reaction of indium plus 1 is spontaneous. Since we have to calculate the value of equilibrium constant for both disproportionation of indium and disproportionation of thallium, we can write that the value of equilibrium constant is equal to 10 to the power number of electrons participating in the net cell reaction into E naught of the cell divided by 2.303 RT upon F, whose value is given here, that is 0.06. So now for the first part, like if I have to write that what is the value of equilibrium constant, that will be Kc here because the ions are there in aqueous medium, and the value of Kc for indium disproportionation reaction will be indium present in plus 3 oxidation state divided by indium present in plus 1 to the power 3. From here I am writing because you can see that this metal is present in pure form, so its activity will be 1. So concentration of this upon concentration of this to the power 3. So this will be the value of equilibrium constant, which we can write here 10 into number of electrons participating in the net cell reaction is 2 for indium as well as thallium. When we are adding, 2 electrons are participating, and we have calculated E naught cell will be 0.315. So if I put the value over here, 2 into 0.315 divided by 0.06. So if I further simplify, I can write that this value is equal to 10 to the power 0.315 divided by 0.03, or this is 10 to the power 31.5 divided by 3. So on simplification, I can write that this value is equal to 10 to the power. This will go 10 times and 10.5, right? And we know that this can be written as 10 to the power 0.5 is under root into 10 to the power 10, which is equal to 3.16 into 10 to the power 10, right? So since the value of E naught of the cell is positive, the equilibrium constant is greater than 1. Similarly, for the second reaction, if I want to write that what is the value of Kc, the value of Kc is equal to the concentration of thallium plus 3 upon the concentration of thallium plus 1 to the power 3, which is equal to 10 to the power, number of electrons again is 2, but the value of E naught of the cell is minus 1.95, this value, right? So I can write here that minus 1.59. 1.59 divided by 0.06. So on simplification, we can find out what is this value. If I write this as 10 to the power minus 1.59 divided by 0.03, this is 10 to the power minus 159 divided by 3, which on simplification we are getting this is 10 to the power minus 53, right? So again, this value of equilibrium constant is very small quantity because E naught cell is negative, and we can say that since E naught cell is negative, the equilibrium constant will be less than 1 and the reaction is non-spontaneous under standard conditions. So the disproportionation of indium is spontaneous under standard condition, while the disproportionation of thallium is non-spontaneous under standard condition, right? And from a standard condition, we can find out from equilibrium constant value, because we are saying that delta G naught is minus 2.303 RT log equilibrium constant. So here they are asking about the value of equilibrium constant. So in first case, this is 3.16 into 10 to the power minus 10. And in the second case, it is 10 to the power minus 53. So hope this whole discussion is useful to you. For more such content, you can download our app where you will get very detailed courses for JEE Advanced. Thank you very much.